Welcome, everybody. As Kat said, thank you so much for taking time to come to the dissertation defense of Momona Yamagami, PhD candidate here in electrical and computer engineering. It's really a distinct pleasure and honor. I'm Sam Burden. I'm assistant professor here in ECE. It's my distinct pleasure and honor to be co-chair of Momona's committee and get an opportunity to introduce her and some of the amazing work that she's done as a PhD student here at the University of Washington. I'll split this intro with her co-advisor, Kat Steele. I'll sort of do, so you'll get both of our takes on what Momona's contributed, both to our groups and to the whole university, really. So I get sort of the beginning picture of where Momona came from and what the path has looked like to get to where we are today. So Momona studied got her BS degree from Rice University in bioengineering. Then she came here starting in 2017 in our PhD program. She got a master's along the way. Also along the way, she got just about every award that we could find that she was eligible for. I'll highlight, starting with a couple of really fantastic fellowships from our College of Engineering and then from our Institute for Neuroengineering, receiving a Best Paper Award from our Center for Neurotechnology, another award from the College of Engineering Student Research Award, and then fellowship in our department. Just these kind of highlight, the external recognition that Momona's work and efforts have garnered. Of course, if you've spent much time around Momona, maybe the first thing that might come to mind, or the thing that the most people might have direct kind of experience and access to, is the way that she's influenced the social dynamics in every group that she's interacted with. From in her first year, she organized a sort of cherry blossom viewing with the whole group. She's taken us on tons of hikes and picnics and rooftop parties and other kinds of fun stuff like that. The thing that I will always remember from these experiences was the karaoke, and I hope we'll get a chance to do this again before you leave, so we can pass the torch and share it with the next generation. The thing that we're really here to listen to today is Momona's contributions to research, and I thought the easiest way to highlight this from my perspective was just to go through and list these archival publications she's finished and published as part of her PhD, and it's just incredible to have 7 of these archival publications by the end of your PhD. I was looking back at my record, and I had 2 when I graduated. So 7's pretty high bar. I tell my PhD students a thesis is roughly 2 or 3 journal papers and a story. So 7 is quite a bit above that bar. Just want the other PhD students to know here, Momona has vastly overachieved in this regard. You do not need to live up to this level or this expectation, but it's just a really amazing, spectacular accomplishment. But the final thing I wanted to highlight, because this is, I've been thrilled and benefited tremendously from collaborating with Momona as a researcher and seeing her develop as a researcher. But there's this whole other dimension to her work. She's had this incredibly productive time as a researcher, but also in really substantively improving quality of life for so many of her peers and students here at our university. This started in her first couple of years here, being an organizer, bringing together, internal and external speakers, building community. She was the president, and kind of, as far as I can tell from talking to students that have been involved around this time, the chief proponent of our grad student association, running all kinds of different events, making people feel more included and supported in the program. A really huge lift. And if you don't know this about her, it's just mind-boggling to imagine her doing this in parallel with all of the other, fabulous research work. She has been heavily involved in our graduate and postdoc student union for the past 4 years, culminating this past year in becoming a head steward. This is one of 12 of these positions across the entire university. She's advocating for she's at the negotiating table advocating for thousands of her peers. She's been really critical in negotiations around trans-inclusive healthcare and cost of living improvements, even during COVID and things like that. It's just really remarkable. And most recently, she served on our faculty search committee a year ago, helping to hire really outstanding new faculty. And I should note, in all of these cases, this is like the first time that any student that served on this committee, this is the first time an ECE person has been, head steward for the union. She's just been a trailblazer and an absolute delight. This is in this capacity that I feel like I've I've learned a tremendous amount from Momona in terms of her research, but in this capacity, in terms of being a leader and in working in service on behalf of others, it's leaves an indelible impact, and it's something that I can only hope to strive for in the coming years in my job. So with that, I'd like to turn it over to Kat.
Let's see. And I just have to echo a lot of Sam's enthusiasm. We're so excited that Momona has made it today. And I think all of these examples just demonstrate that she is a true community builder and really innovative in her research. And whether it's inside or outside, she brings the cherry blossoms and cheer wherever she goes. And I really can't put it much better than our former lab member, Darren Howell, who said, "It was an absolute joy to collaborate with Momona. She's a powerhouse of a hard worker, a brilliant communicator, and someone who has a genuine heart for mentoring the next generation of engineers." And as you see through all this work, she really just brings the enthusiasm. And she also encourages our teams to get out of the lab and into the outdoors, and has taken full advantage of what the Pacific Northwest has to offer and brought her lab members and collaborators along with her. And as far as I know, she is also the only lab member from our research groups to have summited Mount Rainier as well during her time. Just to add one more item to that list of accomplishments. Now, thankfully today, this PhD is just the first stepping stone in what we see as a really fantastic and innovative career for Momona. And we are excited that we will not yet be quite saying goodbye to her at UW. Next year, she will be joining UW as a CREATE postdoctoral fellow, working with the wonderful Jen Mankov in computer science and engineering on a meta grant that they prepared together, looking at more inclusive neural interfaces, where I know she will further grow in her expertise in human-computer interaction and accessibility. And we're really excited as well that following that year, as long as all negotiations finalize accordingly, she will also be joining the faculty at her alma mater, Rice University, in electrical and computer engineering. So we're really excited to see where these future pathways take her. So now on to the main event. Today, we will get to hear about all of this wonderful work that Momona has been doing. At the end of her presentation, there will be a session for public questions. A reminder, the more questions you ask, the fewer she has to respond to from her committee. But it really is an opportunity for us all to learn and grow together. And so we encourage you at the end to raise your hand and unmute. Sam and I can help facilitate and moderate that at the end. And then we will have a closed door, closed Zoom session with her committee after that. So with that, I will turn it over to Momona, and good luck to you today, Momona.
Awesome. Wow. Thank you so much for that introduction. That was really awesome. Let me share my screen. Is everybody seeing the thing that you're supposed to see? Not my speaker notes?
Good.
Yes. Okay, great. All right. Well, yeah, thank you so much for that introduction. That was awesome. I am excited to talk to you all today about everything I've done during my PhD for my dissertation work on modeling and enhancing human-machine interaction for accessibility and health. And if you want to follow along with my slides, there is an accessible version available at the link that I just sent in the chat, bit.ly/Momona-slides. Awesome. So first, I want you to take a second to think about the machines and devices that you've operated today. Have you used a smartphone, or maybe you drove? Do you turn on your TV? You're probably on your laptop or phone right now. And in order to operate these machines, what kind of assumptions are these machines making about your abilities? Maybe the car is assuming that you're at a certain height and weight as a driver, or maybe your smartphone is assuming that you have the strength to hold it and the dexterity to finally navigate all those tiny little buttons. Specifically, your machines are making assumptions and developing models about our abilities so that they can interpret our intended interactions from sensors, like the capacitive panel on the touch screen, a low sensor on a gas pedal, or mouse movement. But who fits into these assumed abilities, and how can we better design interfaces such that the diverse abilities that we see in this world are integrated into the development of these models and sensors? So at this point, you might be thinking, well, why not just design for the average so most people can use these machines? So I'll give you an example from aviation that really highlights the importance of individualization and ability-based design. As Sarah Henda recounts in the book, What Can Our Body Do? In the 1940s, the US Air Force was experiencing a high incidence of crashes during flight training. And when a scientist was commissioned to identify the cause of the crashes, he noted that all the cockpit structures had been built to the specifications calculated for an average military recruit. But when he measured the soldiers, none of the soldiers fit all 10 dimensions that had been considered when building the quote unquote average cockpit. So the conclusion that the scientists came to was there was no such thing as an average pilot. The unyielding fixity of the average cockpit ended up being useful to exactly no one. And after this realization, the engineers began to make everything adjustable to fit a wide range of body measurements so that each person could adjust the cockpit to fit the specifications of their own body. And safety and comfort for the pilots significantly improved. And we do this for a lot of machines and technologies like cars and smartphones as well, but a lot of times only for the physical features like adjusting the height of a car seat or adjusting the length of the watch strap. However, for the cyber and virtual interactions with the machines, like how much force you have to put for the car to go at a certain acceleration or how precise your fingers placements have to be for a touch to register on a touchscreen, still is not adaptable or is difficult to adapt. And that's a wasted opportunity to improve the comfort and ease of use of these machines, not just for people with average abilities, but especially for people with limited motion arising from Parkinson's, stroke, amputation, and other physical disabilities. So the question that I'm interested in investigating is similarly to how the aviation engineers personalized the cockpit in the 1950s, how can we build individualized, adaptable interfaces to customize human-machine interactions for people with and without limited movement? So first, I'll give you an overview of the history of developing individualized interfaces, and then discuss some of the techniques that I draw from in order to conduct my own work. So the 1930s was when the field of human factors started to take off with the goal to reduce human error, increase productivity, and enhance safety. Much of the work here focused on physical adaptation and individualization, such as the ergonomics of a workspace to avoid repetitive strain injuries. Here we note that the range and types of physical adjustments that are available tends to be limited to manufacturer specifications. And when it comes to transferring information from the human to the machine and vice versa, much of the information transfer is what I would consider to be low bandwidth, such as lights or sensor values, like how fast your car is going. Then in the 1970s, with the development of personalized computing devices and the internet, the field of human-computer interaction started to take off, focusing on usability in computing devices. Here, because we are primarily manipulating software, we have a lot more range in how to adapt the software to suit our needs, such as increasing the text size on your phone. And the feedback loop between the human and the machine for HCI is what I consider to be medium bandwidth feedback, such as text or voice. Lastly, industry is currently focused on developing the next generation brain/body machine interfaces, which promises intuitive and always available information transfer between the human and the machine. And much of the information transfer options being considered here involve high bandwidth and multimodal feedback, such as invasive and non-invasive neural interfaces like wearables. And in my work, I adapt models of human-machine interfaces that were initially developed when considering human factors and the safety of pilots flying airplanes, leverage accessibility methods from human-computer interaction, and use next-generation neural interfaces like electromyography that's currently being developed. So at this point, you might be wondering why I have such a strong focus on neural interfaces. There's a couple of reasons for this. One, biosignals, by their nature, tend to fluctuate quite heavily and may require individualized interfaces. And that's great for accessibility because individualized interfaces is one of the tenets of ability-based design. Additionally, biosignals tend to be a little bit higher up the neural circuitry. So what do I mean by this? So let's say somebody might have difficulty controlling a mouse in order to control a cursor on a screen because they had a stroke. And so they're having a hard time sending electrical signals from their brain to their hand in order to control that mouse. However, we might be able to use the electrical signals from the brain directly using non-invasive technologies such as the electroencephalography device that you see here in order to directly control a cursor on a screen, for example. So that's what I mean by biosignals being a little bit higher up the neural circuitry. Lastly, always-on sensors, or sensors that are always on the body and continually providing measurements from the human to the machine, might be useful for continuous health monitoring. And to design and optimize interfaces that can adapt to individual users, we first need to develop and test individualized models for each person. So my PhD work focused on developing predictive models of human-machine interaction and then enhancing those models using biosensors as well as with coadaptive controllers. I also did extensive work on identifying user needs to understand how we can improve the accessibility of human-machine interaction and how HMIs can support health. So first, I'll talk about my work on how we developed the predictive human-machine interaction model using control theory methods, and then how we validated the model by assessing how our human-machine interface model is affected by handedness. Some of the driving questions here were to understand how we can model continuous human-machine interactions and how handedness affects learned controllers. So let me give you an example of how we can model the human-machine interaction as a control system, where the human is the controller that adjusts their input to the machine to achieve a desired result, such as navigating down a path with a powered wheelchair. I'm particularly interested in continuous tasks where people are continually providing input to a machine to perform tasks like driving, navigating a cursor on a screen, or controlling a virtual reality avatar. So let's take this example of a person controlling a powered wheelchair. And let's say the person wants to go straight down to the end of the pathway, and they might implement their intent to do that by manipulating their joystick interface. However, they may encounter disturbances such as needing to avoid hitting a dog and might end up veering left onto the grass. But since the person wanted to go straight and not to the left, this causes an error between where the person is and where the person wants to be, which causes them to do error correction and move back towards the right. And in some instances, error correction and intent might be implemented one after another or in series, but oftentimes for continuous interactions, they're actually implemented in parallel or simultaneously. And in control theory, we can assign variables that relate signals and controllers to each other. So in this slide, we denote the reference, disturbance, and output as R, D, and Y, and the intent and error correction controllers, which in control theory we denote as feed forward and feedback controllers as F and B. And in my work, we simplify this very complex wheelchair control task to be a very simple one-dimensional cursor control task where the person is following a reference trajectory using either a manual input like a mouse or a slider, or a biosignal-based input like electromyography interface. And in this work, the person is being asked to follow a reference trajectory. And in order to track that, we assume that the human has some type of model in mind. And the model that we are going to use is the person does feed forward and feedback control in parallel in order to produce their user input. There may additionally be disturbances in the system, like the dog jumping out at the person, and that's implemented here by the user input being buffeted by invisible forces. There may also be system dynamics, and this is common in mechanical systems. So some examples of system dynamics are the position of your joystick corresponding to the velocity of your wheelchair, or how much you are pressing down on the gas pedal corresponding to the acceleration of your car. So those are examples of first and second order systems. And then lastly, once all these signals go through the system dynamics, we then have the user controlled cursor position. And we can then use block diagram algebra to transcribe this block diagram into a series of algebraic equations that relate the measured and prescribed signals and controllers to each other in the frequency domain, and then do algebra to solve for the feed-forward and feedback controllers under certain assumptions. So next, let's take a simple example of how this works. We can ask important questions like, how does handedness affect our interactions? And this is important because some individuals might have disabilities due to brain injuries like stroke or cerebral palsy that affects only one side of their body. So as they learn or relearn how to use their affected side to interact with machines, it's important to understand and leverage known differences in whether handedness affects human-machine interactions. Additionally, in general, we want to develop an individualized model of human-machine interaction. And it's important for us to understand whether we need to individualize the model to each person, or if we additionally need to individualize it to whichever hand that the person is using to interact with the machine. This wasn't well understood, so we wanted to understand if handedness or the left or right hands affect learn, feed forward, and feedback controllers during a trajectory tracking task. So we looked at this first experiment, looked at whether there were performance differences between dominant and non-dominant hands when performing this trajectory tracking task. And the task that we had our participants do is a combined reference tracking and disturbance rejection task, and they were controlling a second order system. So that just means the position of this cursor or of the slider corresponds to the acceleration of the cursor on the screen. We had two main groups do the same task. One is group RL that did this tracking task with their dominant right hand before their non-dominant left hand, as well as group LR that did the same task with their non-dominant left hand before their dominant right hand. So all of our participants were right hand dominant. Moving on to the results, we can first take a look at tracking error in the time domain. And so here, lower values are better. Let's first take a look at group RL. What we see here is that for the first 5 trials, our participants performed pretty badly, but they are able to quickly learn how to do this tracking task, and they converge to a performance metric and maintain that performance for the rest of the 30 trials. And when they switch hands to their non-dominant left hand, we actually see that this performance improvement is maintained across the rest of the 60 trials. And we see a similar result for group LR as well. So summarizing these results, the light gray box corresponds to the average of the first 5 trials. The dark gray box corresponds to the average of the last 5 trials. And what we see is that regardless of which hand the person initially learned the task with, they're able to improve their tracking error with practice, and whatever they learned appears to be transferred when they switch hands. Next, we can take a look at how feedback and feed-forward controllers adapt. First, we can take a look at how feedback controller magnitude adapts with practice. And what we see here is that the feedback controller magnitude increases with practice, and that increase is maintained when they switch hands. However, feed-forward controllers do not appear to adapt. So in conclusion, handedness does not seem to affect learned controllers, and learning seems to transfer between hands. And in other words, once a person's brain and body figure out how to learn to control that interface, that skill persists regardless of if they switch hands in order to interact with the machine. And this is exciting for future work because this suggests that for people without disabilities, we could potentially train them to learn how to use a novel interface with one hand, and that learning might persist when they switch hands. An exciting avenue for future work is to examine whether the transfer of learning also occurs for people after brain injuries like stroke or cerebral palsy. We additionally found that feedback controllers adapt, but feed-forward controllers do not. And so this had us asking the question of whether we can develop co-adaptive interfaces that specifically assist the person with doing feedback control, so that maybe the person can learn how to do this task faster or more easily. And that's actually going to be the focus of the third part of my talk. Next, I'll discuss some work that I've done on improving human-machine interactions with biosignals. And the biosignal that I'll be using is electromyography. Some of the driving questions here were to understand whether EMG interfaces improve continuous cursor control and how disability affects EMG versus manual control. First, what is electromyography or EMG? For those of you that are unfamiliar, to control a cursor on a screen using a mouse, for example, your brain actually sends electrical signals to your muscles that control your arms and fingers, and the electrical signals can be non-invasively measured using electrodes on the muscles and are called EMG signals. EMG interfaces might improve accessibility and health for people with limited motion because, like I mentioned previously, some individuals have disabilities that only affect one side of their body, leading to decreased use of their affected arm. And this might lead them to only use their unaffected side to interact with technology, such as by using the one-handed keyboard that I'm showing you here. But this could actually lead to challenges with recovery because they are not using their affected arm regularly in everyday life. And in such scenarios, EMG interfaces might be useful to encourage use of the affected arm because even if the person doesn't have the strength or dexterity to use manual interfaces like mice or keyboards, they might still have residual EMG signals to directly control a cursor on a screen, for example. Additionally, electrolocation can be individualized to muscles that people find easier to control or muscles that people might want to improve the function of. For example, some individuals might find larger muscle groups on the biceps and triceps easier to control than the smaller muscle groups on the forearms or the fingers. And if there are specific muscles that people want to practice activating, we can also place electrodes on those muscle groups as well. We wanted to quantify whether EMG interfaces could improve user interaction to potentially encourage use of the affected side and encourage development of long-term EMG interfaces in industry and research. So here I'm showing you a video of a person doing this trajectory tracking task with both EMG and manual interfaces. And the goal of this study was to determine whether EMG interfaces could improve continuous cursor control. So the people are being asked to track to control the purple cursor with either their biceps and triceps or with a manual interface. And in this case, the manual interface is a slider. Moving on to the results, we can first take a look at tracking error in the time domain again. And so lower values are better. We had our participants doing two different types of tasks, a velocity-based task and an acceleration-based task. And what we see with the tracking error is that regardless of the interface that the person is using, whether it's the EMG interface in light yellow or the manual interface in dark purple, participants perform pretty comparably. We can additionally take a look at intent error in the frequency domain, and this is how well people formed their feed-forward controllers in the absence of feedback control. And what we see here is that for the velocity-based task, participants also seem to perform pretty comparably between the two interfaces, but for the acceleration-based task, participants do much better with the EMG interface than the manual interface. So this suggests that for specific task dynamics, muscle interfaces may actually improve performance for some individuals. Next, we can take a look at the same experiment, but now looking at the results from 3 participants who did the same tracking task, but who used their affected arm to do the tracking task. And all these participants have stroke and they are using the arm that they do not regularly use in everyday life. So that's why these 3 dots correspond to the 3 different participants. So first, taking a look at the tracking error again, we can see that our participants who had stroke are now do much worse than our participants who did not have a stroke. However, when we look at the frequency domain metrics, and again, looking at the intent error, how well people form their feed-forward controllers in the absence of feedback control, we see that now our participants with stroke are doing pretty comparably to our participants without stroke, and they seem to be doing a little better with the EMG interface as well. So in conclusion, EMG interfaces may improve intent or feed-forward model formulation for acceleration-based tasks, which suggests that EMG interfaces may be particularly useful for acceleration-based tasks such as driving a car or driving a drone. Additionally, we found that EMG interfaces could improve interface accessibility if we can augment the person's feedback controller. And that will be the focus of the next part of my talk. And so here, I'll talk about some of the work that I've done on developing co-adaptive controllers. Some of the driving questions here were to understand whether game theory can be used to augment the person's feedback controller and what differences exist between co-adaptation and a baseline. So why is co-adaptation potentially useful? Here, I'm showing you a picture of a person doing surgery using robotics, a person walking with a passive exoskeleton, and a person using an invasive neural interface to control a robotic arm. And all these machines that I show you usually assume a little bit more adaptation on part of the user rather than the machine with extensive calibration in place. And in particular, humans have been learning how to adapt to static machines for a long time. So why might it be beneficial for the machine to adapt to the human in addition to the human adapting to the machine? One reason might be due to disability or fluctuating abilities. And this doesn't have to be a long-term disability either. So here I'm showing you a photo of a person who's taking a picture on a smartphone while they're wearing gloves. And in that scenario, you might want your smartphone interface, your touchscreen, to interact with you differently than if you were taking a picture indoors. So that's an example of a situational disability in which you might want your smartphone to adapt and interact with you differently automatically, depending on the situation that you're in. Additionally, co-adaptation might be useful when the user input is highly individualized or fluctuates over time, such as in the case of biosignal interfaces. Co-adaptation might also improve the ease of use and decrease learning time for novices, which is really helpful to use some of these new and emerging technologies that are coming out like VR or AR. Lastly, co-adaptation could be useful to tweak the parameters of co-adaptation to decrease or increase user effort. In general, we do want to decrease user effort so that people can interact with devices more seamlessly. However, there are certain situations in which we would want to increase user effort. So an example of this is rehabilitation robotics, which is the picture that I'm showing you. And here, a person is holding on to a robotic arm and they're practicing reaching tasks. So as they get better and better at doing these reaching tasks after they have a stroke, for example, and they're better able to send the electrical signals from their brain to their hands, we would actually want to increase user effort and decrease machine effort so that the person can continue to recover and regain function. And so that's an example in which we would potentially want the person to increase user effort. So our goal was to leverage game theory methods to quantify the effects of co-adaptation on performance and effort. So here we are considering the human-machine co-adaptation as two agents, the human and the machine, that are collaborating to complete a task. And in this case, we are asking our participants to complete a disturbance rejection task. So that just means the reference trajectory is not moving at all, and the user input is being buffeted by invisible forces. And so because of that, we only have feedback control for the person's model now, because the person cannot do feed-forward control because there is no reference. And then once the person's input is provided, we can then adapt the input with a dynamic machine. And then that goes through the disturbance, system dynamics to produce the user-controlled cursor position. We had two main questions going into this experiment. One was whether people and machines can co-adapt to individualized machines in the first place. And then what differences, if any, exist between the individualized machines versus a baseline. So like I mentioned, the task that we had our participants do is a disturbance rejection task, and people were controlling a non-minimum phase second order system. And we specifically chose a non-minimum phase system because previous studies suggest that non-minimum phase systems are particularly challenging for people to control. We had 4 different conditions that we had our participants do. One was a baseline where G is equal to 1 and it's just a pass through. So the user input is not being adapted at all. And we also had 0th, 1st, and 2nd order machine controller dynamics. So the 0th order corresponded to the machine being a gain. The 1st order corresponds to the machine being a gain with 1 pole. And the 2nd order corresponds to the machine being a gain with 2 real poles. The method in which we did the co-adaptation is first, our participants did a couple of these disturbance rejection tasks with a randomized machine controller G. And here I'm showing you the machine controller for the 2nd order machine controller. Next, once the person has somewhat acclimated to the task, we can compute the human's model or the feedback controller B. And this equation can be obtained by doing block diagram algebra on this block diagram. Lastly, we can find an optimal machine controller, G optimal, that minimizes a potential function P. And we're using a potential function because we are modeling the human-machine interaction as a collaborative potential gain, where the incentives of all the players can be expressed using a single global function called the potential function. And we can use the potential function to optimize for the human effort, the machine effort, and the joint performance of the human and the machine to keep the cursor as close to 0 as possible. Next, let's take a look at some of the results. The first question we wanted to answer was whether people converge to different machine dynamics. We can first take a look at the 0th order machine controller. And here, this white dot represents the baseline. And each of these green dots represent each individual person's machine controller at the end of the co-adaptation trials. And we can see that for the 0th order, our participants converge to a machine controller gain that ranges from about 1.1 to about 1.5. Next, we can take a look at the 1st order machine controller. And again, this white dot represents the baseline. And now we see that our participants converge to a wider range of gains and poles. And similarly with the 2nd order system as well. So it appears that people are co-adapting to individualized machine dynamics. Next, we can take a look at whether co-adaptation affects performance, comparing it against the baseline. First, we can take a look at the time domain error. So again, lower values are better here. And what we see is that for the 0th and 1st order system, for 0th and 1st order machine controller, our participants perform pretty comparably between the baseline and co-adaptation. And actually, for the 2nd order machine controller, our participants do worse with co-adaptation compared to the baseline. So it appears that co-adaptation results in similar or worse performance than baseline. We also looked at a couple of other performance metrics. And I'm just showing you the performance metrics for the 1st order machine controller, but these results are pretty comparable for the other orders as well. So here, the first one, I'm looking at the potential function loss in the frequency domain. This one, I'm looking at the cursor position in the frequency domain. So here we just take the fast Fourier transform of the user controlled cursor position and just pull out the first 2 frequencies that we're stimulating at. And we can also take a look at the system performance that transforms the disturbance into the cursor position. And for all of these performance metrics, we see that co-adaptation has a similar performance to baseline. So at this point, we were a little confused because if participants are having similar performance to baseline with co-adaptation, why are they all converging to individualized machine controllers and why are they not converging to the baseline? And the reason for this appears to be because maybe humans are lazy and they would prefer to do less effort. And so here we're defining effort as the feedback controller magnitude. And what we see is that the feedback controller magnitude decreases with co-adaptation compared to the baseline. And it appears that in order to compensate for that, the machine effort increases with co-adaptation compared to the baseline. And here the baseline machine controller effort is aligned because all our participants have the same baseline. And so it appears that there is a trade-off between machine and human effort, where for this particular experiment, humans prefer to do less effort so that the machine can perform more effort. In conclusion, we did find convergence to different machine controllers despite having similar performance to baseline. And this appears to be due to a trade-off between machine and human effort. And for future work, I hope to design algorithms that seek game theoretic equilibrium points, such as the Nash equilibrium, as well as test parameters to assess the effects on effort and learning. For example, we could potentially increase the penalty term on the machine and decrease the penalty term on the human to force the human to do more effort, for example, such as in the case of rehabilitation robotics. Lastly, I'll switch gears a little bit and talk about the work that I've done on identifying user needs. And some of the driving questions here were, how can we leverage neural interfaces and new and emerging technologies to best suit people's needs? And what are some of the most pressing challenges with human-machine interactions? One project that I worked on was developing therapeutic virtual reality tools for people with Parkinson's disease. And this is a really exciting clinical application of a near future technology that's being rapidly developed in industry right now. And we looked at whether we can leverage virtual reality environments to elicit freezing of gait, which is a gait phenomenon that occurs in Parkinson's disease where people feel like their feet are stuck to the ground. And it's a challenging disorder to live with because it can cause injuries and falls and can be dangerous to people's health. However, it's hard to elicit in the clinic because freezing of gait usually only occurs in certain environments like doorways or hallways. So I developed virtual reality environments that mimicked these environments that trigger freezing of gait. And we found that we were able to elicit freezing of gait when people walked through these environments. And this is exciting as a potential tool to elicit freezing of gait in the clinic and potentially provide a therapeutic effect in a safe environment where there are people to help guard against potential falls. Another project that I worked on was developing a design space to improve virtual reality motion controller accessibility. And this research was done while I was a PhD intern at Microsoft Research. This design space enables the creation of accessible methods for bimanual interactions in virtual reality using unimanual input. And this is important because many individuals with disabilities have use of only one arm, such as people who have a stroke or amputation, but virtual reality right now requires 2 motion controllers to navigate. And VR provides the potential to enable interactions that we can't actually still do in the physical world, such as enabling someone to interact with the virtual reality environment with 2 virtual hands using only 1 motion controller. And we shared the prototypes that we developed with the design space with participants with limited motion and found that while the developed prototypes do present more opportunities for greater access to virtual reality, additional adaptations would need to be made to make the accessibility options truly accessible to people of all abilities. Lastly, I have developed technology design recommendations for improving physical therapy accessibility using wearables. Many individuals with physical disabilities do physical therapy, but it's often challenging to track and get feedback from physical therapists due to lapses in insurance or challenges with physically getting to the clinic. I identified design principles and tensions to consider when developing technology to support physical therapy accessibility and obtain direct input from people with disabilities on how wearables could potentially improve physical therapy access. In conclusion, near future technology like virtual reality, augmented reality, and wearables are potentially useful for improving accessibility and health for people with disabilities. And in particular, biosignal-based human-machine interfaces that provide feedback from the human to the machine could be particularly useful in supporting people's health. However, as we develop these technologies, it's important to co-develop them with people with disabilities. Today, I've given you an overview of my dissertation work on developing predictive models of human-machine interactions and then enhancing human-machine interactions with biosensors and co-adaptive controllers, as well as identifying user needs. Next, I'll briefly discuss my vision for future work that I'm really excited about. So my vision is to optimize the next generation human-machine interfaces towards a more inclusive and equitable society. And optimization doesn't just mean performance. I also want to take into account the preferences of the user, their abilities, and how those preferences and abilities change and fluctuate throughout the days or weeks or years. Traditionally, we tend to develop the interfaces first and then adapt them to be accessible or used for health purposes. An example of this is the Nintendo Wii, where the interface was first developed, and then now it's being used to improve people's health by incorporating physical therapy at home, for example. I would love to see a paradigm shift where we take into account how different people will interact differently with these new and emerging technologies as these interfaces and algorithms are being developed. And I want to achieve this goal by developing individualized, adaptive human-machine interface algorithms for biosignal-based control that support accessibility and health. And I'm specifically focusing on biosignal-based control, non-invasive neural interfaces, because I believe that's the next generation interfaces that are coming out. And I'm particularly excited about the potential for accessibility to improve health and vice versa, and the idea that improved device accessibility equals improved health. And I believe that both accessibility and health areas have an overlapping goal to improve the day-to-day lives of people with and without disabilities and have complementary methodologies that can be applied to both improve accessibility and people's health. And in particular, a huge component of rehabilitation is that neurons that fire together, wire together. But a big challenge with rehab is that it's hard to get people to do a sufficient amount of physical therapy to improve function. But what if we could have people practicing the muscle movements while they're doing leisure or work-related activities by improving the accessibility of these devices? And I would love to tackle such questions with my future work. Much of my past work, my dissertation work, focused on developing the tools that I need to develop biosignal-based, individualized, and co-adaptive human-machine interfaces to improve people's health and accessibility. Looking forward, I plan to work directly with people with disabilities to develop co-adaptive human-machine interfaces that adapt to people's abilities as they fluctuate throughout the day, develop toolkits for scalable multi-channel human-machine interactions, and leverage HMIs to transform healthcare. I won't be discussing my future work further during this talk, but I love to chat further about these future plans at a later time. In conclusion, neural interfaces have the potential to improve health and accessibility for people with and without disabilities. To do this, we require the development of individualized models and co-adaptive algorithms. And as we're doing this, we must work in collaboration with people with disabilities or chronic conditions. And if you're interested in any of the work that I mentioned, or if you want to hear more about my planned future work, please reach out or go to my website where you can find more information. All right, lastly, I want to wrap up by thanking you all for your support. First, huge thanks to my co-advisors, Kat and Sam, for their mentorship and guidance over the last 6 years. I am so grateful for their patience and flexibility as I figured out my dissertation and my future plans. Thank you to my other collaborators and mentors, Amy, who is on my reading committee, Val, Martez, Jen, Itai, and Marcy. And of course, thank you to my past and current steel, burden, and biorobotics lab mates and UW, ECE, and mechanical engineering students for their camaraderie and friendship over the years. Special shout out to Sam Huang for being the best roommate and find a job mate. I am still very amazed that we both managed to find jobs. Thank you to our union, UAW 4121, for the livable stipend and amazing health insurance. And thank you to my climbing and outdoor friends for some of the most memorable and amazing memories in Seattle, including probably the slowest Rainier summit ever. And lastly, thank you to my family, my parents, sisters, and grandparents for supporting me from the opposite side of the world and waking up at 4 a.m. to come to this talk. And thank you to my in-laws. And of course, huge thanks to Edgar for being the most amazing hand/arm model and participating in every single human subject experiment that I ran in grad school. I definitely could not have finished my PhD without your participation. That's all I have for you today. Thank you so much for your time and coming to support me.
Wonderful. Thank you so much, Momona. Big rounds of applause. So we will now offer public questions. So if anyone has a question, feel free to raise your hand. We'll try to, and you can unmute. Any questions? Anyone want to start off? Chet, thank you.
All right, I'll start off with a fun one. Way back to the beginning. First, great job, Momona. That was an absolutely fantastic talk.
Thank you.
Way back to the very first project. I think I heard you at the very end say that if you learned it, say with your right hand, it would transfer to your left hand and vice versa. And can you just tell me more about that? Because I'm a little bit confused. Like, I get it if you learn maybe a dynamic model or something, you have to understand centrally, but it doesn't map to my experience of, say, like, I mouse with my right hand most of the time. I get injured, I switch to mouse with my left hand. It seems like it takes me a while to learn how to do like a fast double click with my left hand.
Definitely. I get this question quite a bit with this particular project, and I think it really just has a lot to do with the time scale in which we're learning these tasks. So just for reference, the time scale that we had our participants do this task is 30 minutes with each hand approximately. And so for that time frame, however much they learned, they were able to transfer it. I definitely agree with you that these types of conclusions don't apply to tasks that we learn over years. So, I mean, using chopsticks or like writing with one hand, that, at least for me, it doesn't transfer to my other hand. But I think that really has to do with like the time scale. At some point, we're probably going to reach a point where that learning of different dynamical systems don't transfer. We don't know what that time scale is right now. And I think that's also something really interesting to look at in the future.
Awesome, thank you. It makes perfect sense. And I was able to eventually learn how to mouse with my left hand, and now they're equally good, but it took like 6 months. So the time scale totally makes sense. Thank you so much.
All right, Alyssa.
Nice job, Momona. This is actually Charlotte calling in to ask a question about your third aim. I thought it was cool to see like the trade-off between like how maybe we get lazy and have the machine like take over for us and still kind of produce the same error. And I was curious if you thought about like motivation as an aspect, like if maybe the user was more motivated to reduce their error, do you think they could reduce it further? Or how you think that plays into those results?
Yeah, so we were actually a little surprised by these results because in terms of user effort, the amount of effort that they would have had to produce in order to do similarly as the baseline is literally just moving a slider a little bit further. So we were actually pretty surprised by these results because these results, I think we would have expected them a little bit more if the person had some type of physical force that they had to overcome. So for example, maybe as we move the cursor, as we move the slider up and down, it gets harder and harder to move the slider. And so we were actually pretty surprised to see that people were still kind of quote unquote being lazy, even though the actual task should not have been, I guess, like physically challenging. I don't think I'm answering your question.
That's okay. That's interesting because I was thinking about it as it being like more challenging. But I guess along those lines, do you think it's possible that the co-adaptation, like I guess in your coding and your control algorithm, does the like machine, could it make it harder for the user because the user doesn't know exactly what the machine's doing? Maybe that could play into it too, that they're just like letting the machine do its thing and then kind of reacting?
Yes, I think it is possible that the machine controller potentially makes it more challenging, especially as we increase the order of the machine. Just because, you know, to some extent, the machine is changing every couple of trials. And so every time it changes, the person has to learn a new task. And, you know, for this particular experiment, We did run some baseline simulations, but we didn't run too many with like more higher order machine controllers. So while we did do some tests to make sure that the range in which we were looking at everything will be stable in closed loop, that the higher order machines could have made it more challenging. And I don't know what's the best way would have been to quantify that. But I think anecdotally, some participants did find like the second order machine controller more challenging than like the zeroth or first order.
Interesting, thank you.
Manishka.
Amazing talk, Momona, and really incredible work. I had a question about your fourth aim, which I know the least about, actually. In some of the qualitative studies that you were running, is there anything that came out that you heard from your participants that surprised you, that you didn't expect, that you might think about integrating into like future design?
Yes, so particularly for the physical therapy accessibility paper, something that surprised me personally was a lot of people talked about insurance as being both a barrier as well as something that they were concerned about. So in terms of insurance as a barrier to physical therapy accessibility, because if you don't have health insurance, it's very hard to get physical therapy. But also when we were talking to our participants about technology, getting data from the participants and into, some kind of device, they were concerned about insurance getting that information and somehow using it against them. And that kind of plays a little bit so I think the implications of that kind of plays a little bit more into policy and all of that, which I guess I don't tend to think about policy too much for my particular work because my work tends to be more theoretical, I guess. But I think this project really got me thinking about how policy plays into research and what we can do as researchers about that.
Great. Shruti.
Mona, awesome job. It's very insightful, and I'm still thinking about the third aim about the co-adaptive controllers piece. And so you said that, if I got this right, that I guess participant converge to their individualized, dynamics, and the machine effort versus the human effort was part of that difference. And when you say individual, did you see differences in amongst individuals in how much machine effort versus human effort, what was the cause of that individuality, and how does that play into designing algorithms from the game theory perspective? Thank you.
That's a really good question. So we didn't look too much into whether there were individual differences in effort. We just noticed that overall there appeared to be a decreased user effort compared to baseline. I think it would be, so something that we didn't do, but we probably want to do at some point is to check is there a difference between people who put in less effort? Does that correspond with better or worse performance? Maybe people who were putting in less work, they perform worse or something like that. I don't really know. I am sure there are these kinds of individualized differences, but that's not something we looked into for this study, but I think it's something that's really interesting for future work. Also, shout out, if you are interested in some of this co-adaptive stuff, Manishka is presenting at NCEC tomorrow, and that's related to my third aim with co-adaptation, so I highly encourage you to go to that. It is a very cool talk.
Thank you.
All right, Benjamin.
Hey, Momona, really great talk, and all your results are awesome. I had a question about your intro, and you mentioned that virtual interfaces are not individualized. And I was wondering what your perspective on kind of the individualization we see on our phones with news feeds or recommendation algorithms, and how can those be used towards your goal of improving health and access?
Yeah, that's a really good question. I think that a lot of times we do tend to think about individualization when it comes to like human computer interactions, like kind of more from like, oh, like let's individualize your Facebook news feed or your news and stuff like that. And I think that's something, a lot of those techniques, I think we could put, I mean, I know there are a lot of challenges with that and, you know, things to overcome, but I do think a lot of those techniques could potentially be incorporated into individualizing the specifically like when I say interaction, I mean like I guess like, I don't know if physical interaction is the right word, but the interaction between the human and the machine. How do humans provide what they want to do to the machine? And I think some of those algorithms could potentially be translated into that, because I think a lot of it tends to be a little bit more manual if we are able to individualize in the first place.
Well, yeah, interesting perspective. Because I was thinking like, you know, like an exercise recommendation or that kind of would be interesting direction. Thanks for your answer.
Great. Well, thank you everyone so much for the wonderful questions. Please join me once more in giving a big round of applause for Momona Yamagami.
Thank you. Oh, and if you're in Seattle, please come to Ravenna Brewing at 4. We are doing happy hour.
To celebrate or commiserate. I'm just joking.
Yes. So see you there.
We hope to see you all there. But with that, yeah, we'll close this public portion and wave goodbye. And then committee, please stay on for closed session. Thank you, everyone.
Bye. Thank you for coming.